All right, good afternoon, everybody. Can I get a sound check? Can you guys hear me okay? Okay, somebody speak back just to make sure I can hear you guys. Jump off your mic and give me a good afternoon. I cannot. 1 second. Try that again.
Hello.
Perfect. Awesome. Thanks, guys. Okay. So today we're going to continue on with our foray into acid and base chemistry, our review. One quick announcement. So if you guys may have seen, there's been a quick update about returning to campus. Right now, UBC has issued a statement that we will definitely be online until February 7th and then reevaluating in the week of the 24th. So again, nothing changing about our current format right now, but it is a sort of a perspective they take it on. We'll keep you up to date as soon as we know anything, okay? Second part, the review part, like what we've been going through here, acids and bases. This week, your acid-base assessment, that's the online practice problem set that is for marks. It's worth 2%. It should open, if not now, later this week. I believe it's actually open today. And you have a couple weeks to complete it. Remember, infinite time, infinite attempts. This is meant to be something you work through. Today, we may start to touch on some of the kinds of problems that you will be doing for that. Definitely by Friday, we'll go through them in detail. So make sure you download the baseline slide deck, have a look through them. Those are the kinds of things we're going to be working on. All right, quick reminder from last class, we had a couple of new definitions we brought up. And I just want to open up with some of those. So, first of all, we have acids and we have bases. What was the definition? Why do we call something an acid? How do we define something that's an acid? Or what's specific in the Bronsted-Lowry sort of definition? Yeah, this is a proton donor. In other words, it will dissociate into something that is protons, giving you some other ionized species. So this would be called our acid. A base is the opposite, right? It is a proton acceptor. If it has a proton, we're going to make a species like this. Now I'm just showing half reactions in this case. Typically what we're going to have is an acid-base reaction where some species is the acid and it is reacting with the base in an equilibrium to make our two new products. So in this case, if we've defined our HA species as our acid, we will form this A-, and let's say this base species here is involved, it's going to make our BH guy. There is a specific relationship between these two guys and these two guys. What do we call that general relationship? So I'm highlighting HA. Yeah, they're conjugates, right? They're conjugate acid-base pairs. And the way we read this usually is HA is my acid because it is a proton donor, making up. See, that's a bonehead move. This is A-, excuse me. A- is the conjugate base of HA. BH is the conjugate acid of this base. So calling something a conjugate just means that they're related by having up or down by one proton, and being an acid or base means that if it's giving up or accepting a proton, what's happening between the two. So it's a bit of a perspective thing. In other words, we can also look at this that if I were to look at this equilibrium backwards in this way, starting from A-, what is A-'s role? If I'm focusing on A-, the equilibrium going that way, A- is what? An acid or a base. Yeah, it's a base, which means its conjugate acid would be HA. Calling something conjugate or not is really just a matter of perspective. If I'm focusing on A-, it is a base. That is its role as it moves through that equilibrium ratio, or that equilibrium arrow. Okay, good. We had one more definition, which was strong and weak. How do we define something as being a strong acid or base or a weak acid or base? There's a numerical quantity we specifically called out here. What makes something a strong acid, for example? Goes to completion. Yeah, we are saying that the acid-base equilibrium constant, Ka, must be larger than 1. Remember, how do I define Ka? Ka is not the whole equation, but just what is an equilibrium constant? That's how it's going to be, right? K is equal to the concentration of our products. In this case, let's call it our A minus, the conjugate base we'd be doing, and our H3O plus concentration over starting materials. In this case, it's our HA only. This expression is what we use to talk about the strength of an acid, and we're saying that this here corresponds to an equilibrium, specifically water acting as the base, some acid we're evaluating, calling our HA, in equilibrium with H3O plus and A minus. This is known as the Ka expression. That's the equation, the balanced chemical equation, which corresponds to this equilibrium constant. So if it's bigger than 1, we're saying it's very, very product favored. It likes to fully dissociate. HA in the presence of water will completely be products. If it's a weak system, then it's starting materials. So weak or strong has to do with if it is a product favored system or a starting material favored system. And the other way we say that generally is that Ka or Kb, those are the two species we're looking at, right? Ka, it's talking about the acid dissociation constant. Kb is the base dissociation equilibria. If it's talking about a strong acid, we're focusing on what the value of Ka is. If it's a strong base, it's the value of Kb. In both cases, the equilibrium constant being larger than 1, product favored, is strong. Those are all synonymous. Likewise, if something is weak, that's a starting material favored one. The Ka value would be less than 1 because it's more starting materials left over. That becomes our cut. Okay, so what we're going to do now is start working through some of these other examples. We've introduced our strong systems. Remember, we left off saying that strong acids, there was a list of them. Those are things like HCl, HBr, HI, sulfuric acid, perchloric acid, right? That's these guys. These are ones you should know on site as potential strong acids. Our strong bases, they're all metals from the very far left-hand side of the periodic table. Sodium, potassium, calcium. And hydroxide, something the OH minus from the other side of the table. They're ionic compounds that when you dissolve them in water form hydroxide. They're effectively, knowing this, how many moles of this we add, we know how many moles of hydroxide we're adding to the system. So, weak acids are systems like this. We have an equilibrium and they are different functional groups, and the reason it makes them weak is since they do not fully dissociate some of that HA species. In fact, a majority of the acid sits as that HA species. The starting materials concentration remains high. So the Ka value from this expression would be less than 1. Something to keep in mind and to sort of build up is keep an idea of what molecules are typical weak acids. Carboxylic acids. Here, this is acetic acid. It's this CH2CH3 system here. We're showing it in this sort of line bond structure, or this ball and stick kind of diagram. This is our starting material, and we're going to abbreviate this. A lot of times, this is the acidic compound, but the HA part, we're focusing on this bond right here. This is the hydrogen and the rest of it, the conjugate base piece that we're going to be focusing on for this equilibria. So abbreviating this down is just a way of sort of going more quickly. Even though the entire molecule, the balanced chemical equation, is shown down here, both in sort of ball and stick, but also in our balanced formula, what we will do is actually refer to this as our HA component, that's this guy, is going to react with water. Now remember, in a Ka expression, water is acting as your base. It's the guy who's picking up the proton. That forms our H3O+. That's the conjugate acid from water being a base. That means if this is my acid, its conjugate base is this ion right here. It's the A minus, would be how I would term this guy, but it's this CH3COO minus system here. That's the A minus component. So the Ka expression for this guy, if we reduce it down, shown fully with the full balanced chemical equation, acetic acid plus water gives me my acetate, my CH3COO minus, and H3O plus. When we actually define that as a Ka expression, products shown here, that's our A minus component and my H3O plus, and the denominator is our acetic acid, the unionized. That's the HA component. So one thing to kind of spend some time on too is to make sure that our generic terminology, calling something HA, A minus, that is just a representation of any species that is a weak acid, strong acid, HA, and its conjugate, A minus, is just the ionized form of that species, right? So get used to that. It doesn't matter if this is CH3COOH or benzene COOH or whatever, right? That general thing we're going to abbreviate as A minus or HA, and that's going to allow us to sort of generalize all the different calculations we're talking through. So the Ka expression that we have here is defined by this products over starting material. What we can do from that is if I have the Ka value, I can calculate what's called a pKa. Now, just like we've talked about pH and pOH, those are the negative log of the hydronium ion concentration. That gets us our pH. pOH is negative log of the hydroxide ion concentration. pKa is, on this again, log type scale, it's the negative log of the Ka, or the equilibrium constant, right? So if we know this Ka value, which for acetic acid is given here, it's 1.8 times 10 to the minus 5, I can define this value here, this pKa value. Now, two things to note. What we've said before, this is a weak acid. The Ka agrees with that. This value here, the equilibrium constant, is 1.8 times 10 to the minus 5. It's much, much less than 1. So that fits. This is a weak acid. That's how we're seeing this in terms of its physical constant. pKa is very valuable because we're putting it on the scale, right, this negative log. It fits within that normal canonical 0 to 14 we're used to seeing for the pH scale, right? What that lets us do is kind of, again, by kind of gut feeling, we can rank things in terms of stronger or weaker based on their pKa values. So two things I'm trying to emphasize here. One, the Ka value is related mathematically to the pKa value. That's the bottom equation. pKa is equal to minus log of the Ka. Meaning, if you have one, if I have the pKa, I can calculate the Ka. That's just either log or anti-log, right? Second thing, if I had two molecules, if I had some acid, let's call this acetic acid whose pKa is 4.7, a different molecule whose pKa was, let's say, 5. Which is a stronger acid? Just based on your opinion. If I have one acid, pKa is 4.7. Another acid, pKa is 5. Which is stronger? Yeah, 4.7. The acidity scale and the pKa scale follow. If you are lower, closer to 0 in terms of your pKa, you are a stronger acid, in the same way that a solution at pH of 0 is more acidic. Varun.
So is pK like related to pH, or is it a different scale?
Well, pH is the scale. That's like, pH is the measure of how much hydronium ion would be in a solution in water or otherwise. pKa takes the physical constant. You know, here, remember, if I dissolve acetic acid in water, I generate H3O+, so they're related. There is a link. But pKa on its own, think of it like a melting point. It is a physical property of the acid, and regardless of dissolving it or not, all molecules that are acids have a pKa. It's a phenomenological property of that molecule that allows us to compare them. There's a couple other pieces when we start jumping into buffers where there's a direct relationship. If I dissolve this species in water that has a pKa, I will get a solution that has a pH, right? But
So
actual pH requires us to know how much we're adding, right? That's the difference.
So is that how they like calculate Ka? Do they like figure out what the pKa is in relation to pH and then work backwards from the log?
Yeah, it becomes either a titration where we measure it, and there's again, if you've ever done a titration curve or titration lab, you can actually pull it off of that graph. The other two is, look at it here. The Ka is defined as the concentration of your two products, your H3O plus and your COO minus, and your starting material. So if I were to throw this into solution, wait for it to come to equilibrium, and I could measure all of those concentrations, I would know the Ka value for that acid, right? So we either do it directly by measuring individual concentrations, or we do it by a titration curve where we figure out what the behavior as we go through a buffering situation is. Yeah.
Oh, okay. Cool.
But think of it, really the best way to think about it is acids have pKa's in the same way that solids have melting points. Okay? It's a property. Charity.
To add on to that question, so why would it be necessary to redefine another constant as pKa when you already have the Ka?
Yeah, exactly. The main one is, if I told you, I've got an acid with a Ka of 1.8 times 10 to the minus 5, how acidic is it? And we go, well, wait a minute. Acidic is on, I usually talk pH, so it's more of a common language affair, right? We are used to, everyone is using something on the pH scale, 0 to 14. So casting it in that same light makes it very quick to compare things. And they're all on this sort of log 10 type one. That's the usual one, is it's useful in this way. And it's just a go-between between the two. Having it listed only as its Ka is a little bit harder to relate to in terms of strength.
Okay, thank you so much.
Make sense? Sarah?
So, if Ka is calculated with, this way, and there's the hydronium, I can't really explain it today. The hydronium is on the numerator.
Yep.
Then how is Kb calculated?
Be the same
Well,
idea, right? The Kb expression, boop, right here, would be coming up from something like this. You need to first define, like before we said an acid in water, where water acts like the base, produces hydronium and A minus, the conjugate base. The Kb expression is some species, the base, reacting with water to make the conjugate acid. In this case, our NH4, that's the conjugate acid of this base, and hydroxide. And as a result of that, its Kb expression is the base, water, and hydroxide, and the conjugate acid, right? So it's different components in this case. Make sense?
All right. So it doesn't have anything to do with the K value formula that we have put down already, right?
Which one?
Like the one that also used like C and D over
This one?
A and B. I don't know, I'm getting confused with the letters, but thank you.
This is the general, any equilibrium. I don't care if it's acid-base, this is the rule that falls, right? The specific equilibrium we're talking about now, Ka is this specific equilibrium. Things that are important here is water acts like an acid in a Ka expression, and hydronium ion is a product. In a Kb expression, water is acting like water acts like an acid here. It forms hydroxide in the Kb expression. In the Ka expression, water acts like a base and forms H3O+. The things that change as we change different base strengths are these other two components, right? Our Ha or A minus. Everybody good? And the same thing goes. Weak bases have Kb's that are less than 1, in the same way weak acids have Ka's that are less than 1. Remember, the important part is a Kb expression, water is your acid. A Ka expression, water is the base. The reason we use that, anybody have a speculation? Why are we defining everything in terms of water? What's the purpose of taking some acid or some base and always comparing it as an ionization into water?
It's easy and standardizable.
That's it. Yeah, water's neutral, but there's lots of neutral things. Triethylamine is neutral, ammonia is neutral. We could choose any base we wanted to rank how strong some acid is, or vice versa. We could choose any acid and rank it against any base. Water's awesome for two reasons. One, it's ubiquitous. I hear somebody in Paris, somebody anywhere around the world can make a measurement with water and it's standardized. We can all agree this is a common reference point. Second thing too is water's special. It can act either as an acid or a base. So it allows us to relate strengths of acids and bases because water, H2O, can either give up a proton to form hydroxide or accept a proton to form hydronium. So it allows us to link strengths of acids and bases into one unified system that helps us to go between the both. So it's those two things. Everybody can agree on it. It's standardized. It's like saying, the Celsius scale starts at 0 because we're referencing water. Very similar in this point too. But second is it has this bidentate, or this sort of duality. It can act as an acid or a base depending on how we're doing the change. Okay, now look at this. If we had an equilibrium like this, and I take ammonia and I put it into water, first of all, what is this expression? Is this a Ka expression or a Kb expression? If you look at what you're forming, species that are involved, right, this is Kb, right? We've got something that forms a protonated species. It is picking up, going from left to right, I'm picking up a proton. This is a base reacting with water to make hydroxide and a conjugate acid, right? When this system reaches equilibrium, what species are present? If I was just going to look into a flask, if I was to snapshot of all the atoms, would I see only hydroxide, only ammonia, only NH4? What is present when this thing hits equilibrium? Which species are in that flask? It's a little bit of a meta question, but yeah, everything you see here is there to some extent. Now we know this is a weak base. Ammonia is a weak base. What does that mean about the Kb, the size of the Kb, if I know it's a weak base? Yeah, Kb is small, it's less than 1. What does that mean about the position of this equilibrium? Is it product favored or starting material favored? Starting material reactant favored, absolutely. Does it mean that there are no products? They're still there, they're just smaller. So the problem, what we're working through here is definitions about relative values. Saying Kb is less than 1 just means the ratio, products over starting materials, is less than 1. There are bigger numbers in the denominator relative to the numerator. It doesn't mean the numerator is 0. There's values up there, they may just be tiny. What we're trying to drive home is when you reach equilibrium, in any equilibrium, there's always going to be some of both of those two species. That's kind of how we define it as an equilibrium. If it was one way, or an irreversible reaction, we generally are saying there is no more starting material and there are only products. So when we call it an equilibrium, even if the values are small on the starting material or the product, they're still present, right? It's still a ratio. It still has a K. And if we divide by 0 or we divide something by 0, that whole number blows up, right? The K value has to exist, meaning numbers have to be in numerator and denominator. So what this means is, and goes back to why we use water, the way we relate the whole system, Kas and Kbs, to each other is by using what's known as the autoionization of water. Water could act as either an acid or a base. So in this specific expression we've given here, you can sort of see it looks kind of like both the Ka and the Kb expression. So I'm going to color code these. So here, let me just jump over to my guy. What I'm saying is, if I take one molecule of water, this red one here, and I take another molecule of water, the blue one, because water, yes, it's neutral, but water has this sort of duality, this presence where it can act as either an acid or a base, I can track this out and say, okay, this molecule of water will act like a base. It will pick up a proton, and it's going to make H3O+. So that means this guy was acting like a base to make the conjugate acid. The blue one was acting like an acid. It loses a proton to form my product, hydroxide, which is my conjugate base. Water has this property where it can exist as both either the neutral species, act as an acid, or act as a base. And this is the two things that we've seen with the Ka and Kb expression. The reason we bring this up, and this is one of the things that makes water kind of special, it has this property where it can auto-ionize, meaning it's sharing the protons among the entire sort of system, around all the waters that are present. Now, if we said the Kw, this is the Kw expression, or this equation here, it's not Ka or Kb, we call this expression Kw, which is the ionization of water. And if you look there, the value for Kw, we said, has been measured at least at room temperature, room pressure, 25 degrees C. Kw is equal to 1 times 10 to the minus 14. What is that? What do you expect now? Is this a product favored or starting material favored equilibria? given this value. If Kw is 1 times 10 to the minus 14, yeah, this is way reactant favored, right? This is a really reactant favored sort of a system. So it doesn't happen a lot. It's there. A tiny amount of it is there. So, this will be definitely, like water spends, all we say from this is water spends most of its time being nice neutral water. Some of it can ionize though, on its own, floating around. Side quest, this comment right here, 25 degrees C. Does anybody know why could a K value change with temperature? This goes back to some basic thermo. You guys may have heard it before. I just want a quick poll from everybody. Does anybody know why a K value might change with temperature?
Reaction rate depends on temperature.
Yeah, reaction rate is part of it. But remember, this is equilibrium, so there's 2 reaction rates, forward and back. If you heat them up, they're both going to kind of change. So there is some of that. What else?
Is it because temperature can like determine the speed at which particles are moving? So like if it's hotter, the particles will move faster, and if it's colder, they'll move slower. Yeah, and that's again a rate argument. You know, moving faster means more shots on goal, more collisions, more reactions. But again, everything moves faster, meaning the forward rate and the backward rate are faster. You're right, that is a part of it. But where the equilibrium, remember, K is where that equilibrium sits. It's the starting materials and the products over the concentrations. If we're at equilibrium, their concentration shouldn't change. There's more flux. There's a lot more of this going on. Yeah, enthalpy and entropy. It comes down to what's known as free energy. The delta G of the system and where that stable state is will change according to temperature. And we'll get into that one next. That's the next sort of piece of it. But no, really good guys. That is a big chunk of it, right? It's the speed is a part of it. The second part is the free energy, how stable either of those 2 states are. Okay, good. So we have this thing. We now have 3 important equations to describe all the systems going on for an acid or a base dissolved in water. We have our Ka, we have our Kb, and we have our Kw. And again, look at this. What value, if I took Kw, what's the value for the concentration of H3O plus or OH minus? Remember, since the equation, the Kw, we gave it as this value here, 1 times 10 to the minus 14, and Kw must equal to your products, that's your H3O plus, over times your, 2 products, over your reactants. Your reactants are all liquids. There's nothing in the denominator, right? Liquid water, there is no denominator here. Which means if I know the Kw is 1 times 10 to the minus 14, each of these values must be the same. You can say it's X and X. That means that the concentration of H3O plus and must equal the concentration of hydroxide, which must equal 1 times 10 to the minus 7. Do these values look suspiciously familiar? 14, 7. What would the pH of this thing be? Yeah, 7. That's why we say neutral water has a pH of 7. Because if you just have water floating around a solution, all you have is Kw. You don't have a Ka. You don't have a Kb. It's just water. So water sitting in there is going to only have a pH of 7. The hydronium ion concentration of pure water, because of the Kw, equals 7. That also means that the maximum scale is 14. This is why when we're talking about acids and bases in water, we have the pH scale. The 7 being in the middle is a function of the fact that we've got this Kw sort of expression. It's not because we pulled it out of thin air. It's based on a physical property of water. So what this now means is we've got the pH, right, our hydronium ion concentration. We've got the POH, the hydroxide ion concentration, and we have this Kw expression. Because of that, all of these are now interrelatable. If I know the pH and the system is in water, I can calculate the POH because pH plus POH must equal P water, right? PW. And that because the Kw of the system is 10 to the minus 14, the pKw is 14. So knowing one or the other allows me to interconvert between the two of them. Same thing for values, right? This interrelationship between the two means that as long as we dissolve something in water, we can now calculate between them. Knowing the concentration of hydroxide gives me the concentration of H3O+. Knowing the pH of the system allows me to calculate the pOH. And we're using this Kw expression as kind of our transistor to sort of to translate between those two. The reason we emphasize this too is, again, given any one piece of these information, you should be able to move between all of them. Being told a Kw gives you, being told a Ka tells you the pKa, which then can tell you the pKb, which can then tell you the Kb of a system. You can move between each and all of these different systems when you dissolve them in water. So that's the tricky part about this, right? The thing is, there's a lot of ways of communicating the same information. And that's what working through acids and bases is about, is listen to what you've been given, relate that to the definitions you know, and then use the other information you've got of how things are related to calculate a new value. Knowing one piece of information plus these fundamental constants allows you to sort of move in a very wide variety. The other part too is it means that if I know something about some system, an acid is a super strong acid, I can define something about its conjugate base. If any system is a really, really strong acid, its conjugate base must be very weak. There's this equal and opposite pairing because of that. What that means is, if I told you HCl, now you know something about HCl, is it a strong acid or a weak acid? From what you guys know before. Yeah, it's a strong acid. That's one of the guys that you guys have heard on before. So HCl, we know it's strong. We know that the Ka of that system must be much larger than 1. We know that the pKa for this value would be what? Do you guys, if you had to guess, let's say the pKa is much, much bigger than 1. Sorry, the Ka is much, much bigger than 1. The pKa, is it going to be close to 14 or close to 0? If it's a strong acid, yeah, it's going to be somewhere down at, it's going to be low, right? That's a strong acid one. These are all things by just knowing this is strong, we know something about this, we know something about that. The conjugate base of HCl is Cl minus. What does that mean about its strength? If I know that HCl is a strong acid, what can I now infer about the conjugate base of a strong acid? Yeah, it has to be weak, right? The way we could visualize that is we're saying, if I took HCl and I add it to water, we say that all of it, will ionize. We're going to make a lot of H3O plus and Cl minus. Now we originally said, look, this is irreversible. It's all the way over there. We're making only products. If we define this as an equilibrium, we're still going to consider it where there are all species present when it reaches equilibrium. It's just really, really, really product favored. So if it's super product favored, we made chloride. The question I'm asking is, does chloride want or like, or is it favored to go back to starting materials? Does chloride act like an acid? And from this equilibrium, we'd say no. If HCl is pushing super hard, it is product favored, it also means that Cl minus is not going to do a really good job of pushing back, right? We are going to form H3O plus and Cl minus. So visually from the equilibrium, we're saying the same thing. If HCl is a strong acid, Cl minus must be a weak base because the equilibrium favors H3O plus and Cl minus. If you gave Cl the choice, it will want to sit as Cl minus and H3O plus, not reform. What will the Kb be? Yeah, what do you think? Good point. pKa of a strong acid will be close to 0. What do you think the pKb will be? Yeah, it's going to be, it'll be higher on that point too, exactly. And you can calculate them through, right? We can go back and forth between the two of them because of this. The pH and the pOH is on the scale of 14. If the pKa was, yeah, exactly. pKa plus pKb must equal pKw, which is also your 14 value, exactly. So we can fill in and move between the two in that way. All right, good stuff, guys. What that means now is we've got a ranking system. We can look at all acids and all bases, and if I know something about one species, it's inferring or telling me something about another. the hydronium ion, that's our strongest system, that's our baseline, is a very, very, very strong acid. It's right here on the table. What that means is the hydronium ion's conjugate base is water, which is a very weak base. Super strong acid, weak base. And likewise on the other side, water, if it was to act like an acid, it's a very weak acid. Hydroxide is its conjugate base. Hydroxide is a very strong base. And we're talking about, when we say strong and weak in this context, we're doing a comparison of where that acid-base equilibrium is, right? We're saying that for hydronium, it would rather be an acid much, much more than water wants to be a base. In an equilibrium that's competing those two, hydronium is going to win. It also lets us rank up and down. Because of the way that this scale is ranked, right? If I can rank the acids from strongest acid down to weakest acid, so H3O plus down to water, if it's closer to being like a hydronium ion, that is a stronger acid. If it's closer to being like water, it's a weaker acid. And remember, what we're adding here now is this suffix ER. It is a comparison between two different species. Now, this is a really important thing to pay attention to. We are not saying that acetic acid is a strong acid. Acetic acid as compared to ammonium, this one here. So acetic acid compared to ammonium, which one is a stronger acid as a comparison between 2 points? Right. Now this is what throws a lot of people. I'm not saying acetic acid is a strong acid. If something is a strong acid, what am I saying about its Ka? That is a statement about a Ka. If something is a strong acid, the Ka must be bigger than 1. Right. If something is stronger than something else, what am I saying about where they are on this table? Closer to, if species is a stronger acid than some other species, it is closer to hydronium, H3O plus, relative to the other. It's a ranking between the two, right? So yeah, exactly. So that's the thing, don't get thrown off. We will be considering cases later in this course of protons where the base is so strong, if you actually opened the vial in normal open air, it would catch fire. We're talking about acids in some cases that are so strong it would melt glass and stuff. But because we're going to start working outside of the normal sort of 0 to 14 scale. And under that context, saying something is stronger than something else is a relative measurement between two values that fall on this kind of a scale. So like we said before, if I was going to look at these two, HF and HCN. Now, in our context, both of these, their Kas for both HF and HCN, individually, both Kas are less than 1. So if I'm just thinking about HF and I just think about HCN, are they strong acids or weak acids? If individually their Kas are less than 1. They are both, individually they fall in the category of weak acids. But comparing between the two, HF is a stronger acid than HCN. And by making that definition, I now know something about their conjugate bases. Cyanide must be a stronger base. Cn minus is a stronger base than fluoride. Fluoride is a weaker base than cyanide. Okay, so we have these comparative values, we have absolute values to consider. How's everybody feel about that? Cool. Again, we'll repeat this part through, but most important thing to do is always focus on relative values versus absolutes. All right, quiz poll 1. Of the following, which is a strong acid? All right. You have 5 more seconds. All right, and time. So yes, D is the right answer. If you go back and look at each of these species and you remember them in terms of are they going to be strong or weak, These are going to look at the sort of the table, the ones that you've used to. HNO3 is one of those guys that you should remember on site as one of your canonical or one of your normal sort of strong acids. If you go through this and discuss it too, right? If we're ever doing it by elimination, you know, some of it is recognition. Where have I seen this guy before? Some of it is, could this thing act like an acid or a base? Now, first of all, looking down this whole list, does every one of these molecules have the ability to be an acid? Let's start there. Could these be acids? Well, remember, what does it mean to be an acid? Yeah, they donate a proton, right? They donate a proton. That's all we're trying to say. I'm not trying to say who's good at doing that or who's bad at doing that, but do they all have protons they could donate? The answer is yes, right? They all have hydrogens. Then we can sort of break it down and say, well, which is most likely? Which is stronger at doing that? And absolutely, HNO3 ranks in that. E, you guys should remember that. That is your prototypical weak acid, your carboxylic acid, COOH. KOH looks weird because, yeah, if that became an acid, what would your product be? If KOH acted like an acid, what's going to happen there? Yeah, KO, which is, it knocks that one right out, right? There you go. Okay, sorry. But yeah, and it's also going to be O2 minus at that point because K, remember, that's your potassium. That is a positive one charge. That's a very high energy species. The important thing as we start to talk about all these things is not, there's two kind of questions you always think through. Could a reaction happen, which is basically asking, do you violate the rules of atomic bonding and changing where bonds actually are? And the second one is it likely to happen? That's, am I making something stable? Am I forming diamond by just pressing carbon together? That's the reaction class of things. And we'll get into that a lot more as we go through. But the thing is always to separate those. What are the violations of pure physics? And what are the violations of, well, we need a lot of energy to do that? You know, in the context of whatever's going on here in the world, we have sort of a very limited view of things. My brother actually works at JPL. Does anybody know what JPL is? Jet Propulsion's lab. I like to talk like all the robotic stuff that we get to do. Every time I show him something cool I'm going to do, he comes back with something like, yeah, you know, today we signed a panel that we're shooting to Mars. It's no big deal. So he's a lot cooler than I. My point is, some of the chemistry he has to look at is in the lens of what happens on the universe scale, right? So even this thing of looking outside of what happens in water starts to get really, really, really epic. You still can't violate physics, even in space. All right. So the last point we're going to talk about today is this idea of being at equilibrium. All the values, the Ka, the Kb, the Kw, those are equilibrium constants of a species. And like we said before, it's kind of like a melting point. It's a fundamental property of a molecule. What we have, though, is this other value we call the reaction quotient. It's related to, it's similar to an equilibrium constant, and it's useful for measuring where we are on the continuum of I just started the reaction, we are not at equilibrium yet, and I am at equilibrium. Think about it like this. If I take water and I'm going to dissolve sodium chloride into it, at some point a saturated solution of sodium chloride cannot dissolve any more salt, right? It's at equilibrium. There's still going to be solid, there's going to be solid sodium chloride in solution, but there's still molecules moving. It's a dynamic equilibrium. But if I took pure water and pure sodium chloride, mix them together, it is not at equilibrium yet. Some salt has to dissolve. We need to reach that equilibrium position. The reaction quotient allows us to make a measurement of where are we? Are we at equilibrium? Are we approaching equilibrium? Do I need to go forward or backwards to reach the equilibrium value? So it's a useful concept, and we'll reiterate on this a couple more times as we start going through thermal, but I want to introduce it to it now because it allows us to look at a spot or instantaneous change of a system. We define Q really, really, really similar to how we define K, right? It has the same equation, right? It's products over starting materials. That's how we define Q for a system. The only difference between Q and K is the value of these concentrations when the system has reached equilibrium. We're defining it as this is equilibrium, and it's the concentrations above and below, products over starting material, when equilibrium has been reached. Q are the values of concentration At some point, we set the system up. I just throw sodium chloride into water. It is not at equilibrium yet, but it's an instantaneous value of it. So what this lets us do is say, look, if I know the concentrations at some time point, it may or may not be at equilibrium yet. And the way I use that ranking is when Q, the values, numerator and denominator, equal the concentrations of equilibrium, Q equals K. So when Q, the quotient, equals the K value, we have reached equilibrium. If they don't, if they're not there yet, Q does not equal K, we are not at equilibrium yet. So it's a strict value at that point. Another way to look at it is any sort of if we did this by sort of a dynamic reaction, looking at the change over time. I'll pop that actually, we'll do that, we'll come back and touch this one next time because it's actually something we use very heavily in my lab as we do reaction kinetics. We monitor concentrations over time, and what we're asking is, at this instant, at this time point, if I could measure the concentrations of starting materials and products, do those values, does that ratio equal K? If it doesn't, you're not at equilibrium yet, the reaction must continue. If it does, you have reached equilibrium. There's no point in waiting anymore. You have reached its equilibrium value. Knowing this is important for when you make a measurement or how you do a sort of thing. Back to what we talked about measuring the pKa of a system. I could take an acid, dissolve it into water, but if I don't wait until Q equals K, I'm not at equilibrium yet. I'm not actually measuring the pKa. I'm not actually measuring the Ka value because stuff is still happening. We're dynamic. Yeah, exactly. Yeah, exactly. Ks are given to you, right? That just like we're not expecting you to know, oh yeah, definitely acetic acid's K is blah. These are constants of a system. The other way you can do this too is actually pull it out of online. They're physical constants of a system. So, last concept to land on for today. If we dissolve something in water, we've talked about strong acids, strong bases, weak bases. We can now calculate or move between pH, pOH, pKw. If we dissolve salts into solution, though, not all salts are what are called innocent, right? They may have a property where they actually can modify or change the pH of a solution. And the way we look at this is sort of the flip side. If I were to dissolve, let's say, acetic acid in water, what would you expect? If I took acetic acid, which we've defined right now as a weak acid, so CH3, COOH, and if I dissolve it in water, do you guys think that the pH is going to go up or go down? Yeah. Remember, water, if it's neutral, you're sitting at 7. The pH of water should be 7. If I take acetic acid, I dissolve it in water, remember that's our value. We could calculate the Q for that system, which is at some instant, how much products do we have over how much starting materials do we have, right? That could be a value we could measure. But when it reaches its equilibrium position, we know that it's going to make H3O plus and CH3, COO minus, the conjugate base. Some of these guys will exist. This guy will ionize to form this. And we've also said before that this is a weak acid, meaning we believe the Ka for this system is going to be some value which is less than 1, right? It's going to be a starting material favored system. These are phenomenological things of it. But this is easy to spot. We look at a molecule like this and say, that's an acid. It has a proton. I'm dissolving it into water. Therefore, I know the solution is going to get more acidic. Same thing as if I took sodium hydroxide and put it into water, what do you guys expect? Get more acidic or get basic? Higher or lower pH? Yeah, you're throwing in hydroxide, right? We know we're going to be pushing up the concentration of hydroxide in the solution. The other way to say that is we're using up or we're reacting some of the hydronium ion concentration, the pH should go up. But if we have systems like what we're showing here, lithium chloride, and we throw that into water, the ions that you have of salts can sometimes affect the pH. It could make this system go up, it could make it go down, or it could do nothing. So there's three basic pieces to this. Lithium chloride, if I define this right now, I'm going to tell you it does nothing. A solution of lithium chloride is neutral. However, these other two guys, they do something special. The next guy, CH3COOK and CH3NH3Br, these guys are what we call non-innocent. So we're going to work through different pieces of this. And what I want you guys focus on too is the piece I've underlined here. Lithium chloride is made up of, remember, if I was to dissociate that, that's how I would sort of break up the ions in this system. Ionic bonds, right, are made of atoms from very, very far parts in the periodic table. So something from the very left-hand side and something from the right-hand side. So lithium chloride is made up of lithium and chloride. And if I had to assign charges, lithium is what? Plus or minus, or chloride is plus or minus? Lithium probably, yeah. Lithium's going to get the plus charge. It's from the left-hand side of the table. Chloride's going to be the right-hand side. So what we're really doing is saying, okay, if I have lithium and chloride, those are potentially conjugate acids or bases of some other thing, right? In the same way, if I was going to break up this molecule, I identify it and say, look, right here, I have potassium and the rest of this junk. So I'm going to break that up as CH3COO minus and K plus. Does anybody have any... Does that hurt anybody? Do you see why that sort of division is where I make that line? If you look at the other molecules, right? Carbon, hydrogen, oxygen, they're close together on the periodic table, right? Same thing in the bottom example. If I was going to take CH3NH3, I would divide this up as CH3, NH3, and Br. Now, what would the charges be in this bottom case here? Who gets plus and who gets minus if I split them the way I have here? Yeah, Br minus, remember that's your halogen from your extreme right side, which means default, this has got to be positive, right? You're going to do a heterolytic split of where those electrons go. So these are how I do ionizations, and I do this by looking at the periodic table and identifying common elements which are either cations or anions. So yes, salts in this one's typical anion salts, those are going to be things from the extreme right-hand side of the table. Br minus, Cl minus, F minus. Typical positives, those are going to be sodium, potassium, lithium, right? Things from the extreme group 1 in that case. So what we have to do when we look at these and rank them in terms of are they going to be non-innocent, we look at the ions that are being formed and we say, hey, are those ions conjugate acids and bases of weak acids or bases? We have to look back through and say, do I recognize these? So I'm going to do a test. Let's start with lithium chloride. So I'm going to be checking lithium and chloride. Okay, lithium is positive. Does that mean it's going to pick up or lose a proton? If I put lithium chloride, in both cases, I'm going to put them in water, right? So this guy right here, if I took lithium and put it into water and something has to ionize, what pairing am I going to usually pair against this positive charge, right? If lithium is positive and I'm playing with water, yeah, I need a negative charge, right? So I could think of this as, okay, well, that's kind of like making lithium hydroxide, right? Is the species I'm trying to form. I'm saying actually a better way to look at this is, if this is lithium plus, his partner in an acid-base equilibrium should be hydroxide. This guy down here, if this is negative, the partner I'm really wanting to play with would be H3O plus. If it's negatively charged, it's looking for a proton. So its one would be HCl, and water for balance. Okay, look at these two. Do you recognize this? What is that guy? Something should be jumping about the species of, wait a minute, I know that on site, that is what? Yes, this is a strong base. What about this? HCl, you should know that guy on site. This is a strong acid. So what I'm saying is, if I put lithium in water, it should associate, since it's positive, it'll associate it with the negatively charged part of water, hydroxide. And because if that was going to form ionic bond, it's a strong base, meaning it's going to want to be this side of the equilibrium. That first equilibrium, I'm not going to be very product favored. If lithium was going to fall into water to pick up hydroxide, it would just dissociate again. So there's really no reason for it to form lithium hydroxide. Same thing for chloride. If I put chloride in water, it's negatively charged. It wants to interact with the positively charged species, the hydronium, but that's going to have to form HCl. And we know, since it's a strong acid, starting material favored as it is drawn here, right? I'm asking if chloride was a conjugate base, would it be a strong conjugate base? The answer is no. Both of these two guys are not going to significantly change either the hydroxide ion concentration or the hydronium ion concentration. It's not going to do anything. So therefore, lithium chloride in water is neutral. In other words, if I throw lithium chloride into something that's pH 7, it's not going to change the pH of the solution. Nothing can be changed at this point. Would it be possible for innocent ionic compounds to dissociate, form a new insoluble compound? It could, right? But that's where it has to form some other ionic compound. It could react with plain water. But again, if lithium chloride was going to react, it's really what we're doing is we're checking how does lithium plus, what is its new ion going to be? If I take lithium chloride and it splits up into lithium plus and chloride minus, I'm asking what other ionic species is going to actually sort of push this against this. And yes, you're right, that both lithium hydroxide and HCl are strong acids and bases. What I'm saying is, if I just give chloride to a system, it is not going to form a strong acid. It will immediately dissociate back to the Cl-. Remember, when I started this analysis, I'm starting with these species. And I'm asking if I add only this to water, will the equilibrium move towards the products? The answer is no. If I only add chloride to water, I'm not going to form HCl. If I only add lithium to water, I'm not going to form lithium hydroxide. So I'm not going to change the concentration of lithium or hydroxide. It is completely innocent. Let's do the analysis of the second one. CH3COO minus and potassium. So like we did before, if I take both of these systems, since this is negative, I'm going to react it with the positive ionic component, H3O plus. And if I take this guy and react it with its negative component, the hydroxide, once again, this one should jump out at you. This is our KOH. This is a strong base. And because of that, because I would have to form a strong base, if I were to add these species, the equilibrium lies in favor of the starting material. This is not going to do anything. So potassium is innocent. It's not going to change anything. This guy is non-innocent. You guys should remember this point too. If you look at that, CH3COO minus, where have you seen this compound before? What is that compound? It's related to something you've seen. Yeah, it looks like acetic acid. More importantly, what is it related to acetic acid? Related to acetic acid, it is what? Yeah, it is the conjugate base of acetic acid. It's not acetic acid, it is the conjugate base of acetic acid. Which means, if I take CH3OO minus and I add it to my not so crappily drawn hydronium ion, I have an equilibrium where I'm going to form CH3COOH and water, right? Does anybody recognize this equation here? Where have we seen that part today? Acetic acid here plus water gives you H3O plus, and yeah, that is the reverse, drawn backwards, of the Ka expression for acetic acid. If acetic acid was put in water, you make H3O plus and the conjugate base, CH3COO minus. That is an equilibrium we know something about. we know that there's going to be a population here, and more importantly, it's going to want to go which way? This equilibrium as drawn, is it going to be product favored or starting material favored? As it is drawn here. Right, it is product favored. Remember, let's draw this out again. Let me draw this one more time. What we are considering is CH3, COO minus, reacting with the positively charged component, H3O plus, in an equilibrium to make CH3, COOH, and H2O. That looks like, and if I draw this on my normal Ka expression, I would normally look at this as CH3, COOH plus water. I'm just going to reverse it to give me CH3, COO minus, and H3O plus. And let me color code things. These two species are just over here. These two species are over here. They're the same expression, I'm just writing it left to right. When I talked about the Ka expression, we said acetic acid was what? Strong or weak? Yep, this is a weak, which means Ka is what? Bigger than 1, less than 1. Yep, it's less than 1, which means this equilibrium as drawn favors starting materials, right? If I invert that, these are my favorite species. The products are now favored. And as a result of that, this equilibrium will have some of that value. I'm going to actually use up some of this H3O plus, which means I'm forming this product. Okay, we're going to stop there. We'll jump off from this point and we'll talk about how we can use this to calculate the pH of new systems on that point. Thank you so much, guys. Sorry we ran right up to a minute long. All right, talk to you soon.